It was not a very difficult. It was pretty much easier than the Laplace equation. So I was waiting for Yvonne. Hi, Yvonne.
Hi.
We were waiting for you. You are expressing to take class.
Okay.
Actually, I was saying that tomorrow
Okay.
I will revise the remain problem little bit and the topics which you feel difficult. So please take a look at the unit 2 and tomorrow I will completing the heat equation and we can revise little bit the topics just for the sake of convenience, for the sake of clarity. Yeah, so that's why I was waiting for you so that I can
Okay.
yeah. So please revise once because tomorrow I'm gonna just recall all the things and rather than focusing on more calculation we will be focused on more the geometry, how dx over dt is becoming infinite, how it is becoming parallel to x-axis, how like basically we are going to talk about the very basic of real analysis, isn't it? We use a lot of real analysis in unit 2. So it was very basic of real analysis, and I will focus over that because what I feel that Ivan was feeling difficulty with ds over dt equals to u, which we were taking, and how we are plotting those graphs. So I will revise that things, and it is going to be easy. Don't worry.
Perfect.
Yeah. So please don't miss at tomorrow class.
Okay. I will attend the class. No problem.
Yeah. Let u be continuous for x belongs to R and T is lying between capital T to 0. So basically every time when we talk about the heat equation, we fix a time, like the final time is going to be this capital T. So we fix a time almost every time and let ut comma ux and uxx exist and be continuous for x belongs to R and this. Assume that ut is equals to uxx and u of x comma 0 equals to z of x. This g is assumed to be a continuous function. That's why when we are talking about the continuity of ut, ux, uxx, we are talking about the continuity except t equals to 0 because at t equals to 0 we have the function that is the only function of x because time is taken to be a fixed time that is 0 and that is a continuous function and u x t is greater than or equals to 0 and we are also assuming that u is greater than or equals to 0. Then Wheeler's theorem say that in the case of the non-negative solution of this heat equation, in the case of the non-negative solution of this heat equation, which is defined for the fixed time range 0 to t, the solution is uniquely determined and it is represented by the heat kernel. Then U is determined uniquely and represented by u of x comma t is equals to r k x y t z y dy. So you can see that at t equals to 0, this is the initial condition. It means the condition at time t equals to 0, the initial condition is supported by this kernel. And what is the property of this kernel? Heat kernel. In the case of one dimension, since we are taking it in one dimension, so that's fine. K dx like this is equals to 1. So this is the property of the heat kernel, that it is normalized over the space. It is normalized over the space. So let's start the proof of the theorem. So what is the Wieder's theorem? Two things to keep in our mind when we are going to prove the Wieder's theorem. Firstly, that all the derivative which is used in this heat equation, that is ut, ux and uxx, exist and they are continuous. And also ux comma t, that is the solution of this heat equation, is non-negative. Non-negative, we are talking about the non-negative solution of the heat equation. In the case when we have the non-negative solution of the heat equation, then u is determined uniquely and it is represented by this formula, like it can be expressed in the term of heat kernel uniquely. And the most important thing here you need to be aware of, that every time when we talk about the unique heat solution, every time in the previous classes when we talk about the unique heat solution, what was the first criteria? Can anyone tell me? To discuss about the uniqueness of the solution of the heat equation, what was the necessity?
The domain must be bounded.
Domain must be bounded, but is there any restriction on the domain? No. So the Wieder's theorem is like it is expanding the solution, and here we don't have a restriction on the domain. What is the restriction? That we are talking about the non-negative solution of the heat equation. In the case when the solution of the heat equation is non-negative, then in that case we can also express the solution in the terms of the heat kernel. So either, now you have to deal with the two conditions. Once, if you have bounded domain, and if you have non-negative solution. Heat equation, bounded domain, non-negative solution. In those two cases, you are going to get the unique solution of heat equation. So if this condition is satisfied, then fine, we are going to get the unique heat solution. If it doesn't satisfy but this is satisfied, still we will be getting the unique solution of the heat equation. So always keep in your mind, keep maximum principle. So using the strong maximum principle, prove the uniqueness of the heat equation. Why we use the strong maximum principle? Because to use the property of maxima or minima, we need a defined boundary. We need a bounded boundary. In that case, we can define the maxima or minima on those boundary. If the boundary is unbounded, then we cannot use this strong maxima principle. And later on, Witters gave a theorem that is talking about the uniqueness of the heat solution for the non-negative solution. Okay, so this was 2 to 3 things to keep in your mind. That's fine. So to prove these things, now this may be positive or maybe negative, we don't know. So the thing is that u is taken to be greater than or equals to 0. We will prove two things. Firstly, uxt is greater than or equals to this, and then we will prove in the second part that u is exactly equals to this, that is, this quantity is going to be positive. So to prove this theorem, we need two assumptions. We need to prove two identity since U is assumed to be the non-negativity solution of the heat equation, and we don't have any idea about these things whether it might be negative or positive. So we have to prove that U is going to be greater than or equals to this quantity. It means we are talking about the smallest non-negative solution. And in the second half of this theorem, we will prove that if we are assuming that W is a variable defined as u minus this, then w must be identically 0 on the defined domain for the equation ut minus uxx equals to 0. And as soon as we will prove that w is identically 0, it means u is identically equals to this quantity. It means u can be expressed uniquely in the terms of the heat kernel, where the solution of the heat equation is defined with the support of this initial condition using the heat kernel. This quantity is basically known as that the initial condition is supported by the heat kernel. Every time remember, and when we talking about the Laplace equation and this is boundary condition, then we say that the boundary condition is supported by the Poisson kernel. The initial condition for the heat equation is supported by the heat kernel. The boundary condition of the Laplace equation is supported by the Poisson kernel. Always keep in your mind, this is the way how we pronounce. For a is greater than 1, define function zeta ax by zeta ax equals to 1 for mod of x is less than or equals to a minus 1, zeta of ax equals to 0 for mod of x is greater than or equals to a, and zeta of a equals to a minus mod of x for a minus 1 is less than. So since we are taking a is greater than 1, so let's plot this. Suppose I am taking just a parabolic cylinder, because we know that this equation is, what is this equation? Is it elliptic, hyperbolic or parabolic? Is it
Parabolic, right?
sorry?
Parabolic, right?
No.
Because the coefficient c.
Is it hyperbolic? How you are saying that? What is the condition for the hyperbolic? If
The
a,
discriminant and the coefficients of the partial derivatives
yeah, so this is the equation, or let's say
greater than 0 equals to 0 and less than 0.
b square minus 4ac equals to 0 means parabolic. B
Yeah.
square minus 4ac is greater than 0 means hyperbolic. Rest is elliptic. So if you will take a look at this, so what is b? 0, because the coefficient of utx is 0, isn't it?
Yeah.
What is a? 1. If you write it in the form of uxx minus
C squared or v squared, I don't know, the alpha.
sorry,
A must be -1, I think, no?
a is minus 1.
Yeah.
What is c? C is 0, isn't it?
Yeah.
So b square minus 4ac is basically coming to be 0 because b is 0. So isn't it parabolic? Yvonne?
Yes.
Please don't forget this thing because this is the very basic of the parabolicity and hyperbolicity and ellipticity. Because you might be asked, check whether the given equation, the second order given partial differential equation is parabolic, hyperbolic, or elliptic. So please don't miss this part. It's very important, I think. So this domain, like this solution, this ut minus uxx is a parabolic equation. So we are plotting a parabolic cylinder just for the sake of our convenience. We are defining that the solution is defined on the parabolic cylinder because the form of the solution is going to be parabolic. So this is your parabola. Now assume that a equals to 2 because a is greater than 1, so we can assume, like, just assume. I'm just giving a physical representation, a geometrical representation. A equals to 2, then mod of x plus 1 is less than or equals to a. So and a equals to 2, if we keep it equals to 2, it means we are drawing a cylinder, a ball inside this cylinder with radius 1. So zeta ax equals to 0 outside of this a. This is the inside of the cylinder where zeta x is defined to be 1. Outside of this a, zeta ax is 0. And zeta a of x equals to a minus mod of x for the radius. Like suppose if you are taking a equals to 2, then a minus 1 will be like this, the half of this. So inside this portion, I am a very bad printer. I just made this mess. So inside this, zeta of ax is defined to be a minus modulus of x. So this is the geometrical representation. This is with one radius. If I am taking a equals to 2, then this is going to be 2 and the rest are the outside of the cylinder. Now consider the expression y zy dy. According to our assumption, this function is bounded since zeta of ay zy is bounded, and as per the definition of zeta of ax, if you will write it just this form, so you can write it in this way. Just take a look. Zeta of ax is equals to 1 when mod of x is less than or equals to a minus 1, and a minus mod of x when a minus 1. Just a minute. Yeah, I was earlier, I was, yeah, now it is fine. And then 0, then mod of x is, can anyone check whether the order is written correctly or not?
What's the question?
This order, this domain is defined correctly or not, I was asking. Like a minus 1 when mod of x is lying between a minus 1 to a minus a plus 1 to a minus 1. And then a minus 1 to a. Yeah, it's defined correctly. I was just checking. I am writing these functions.
Oh, okay, yeah, like the domain of the cylinder.
Yeah. So you can check it. This will be coming as a continuous function. I was just writing it to, I know that it is continuous, but it is the part of your homework that you can check whether it is a continuous function or not. So you may check it because as soon as modulus of x will be a equals to 0, so the left boundary will be maintained, and as soon as when modulus of x equals to a minus 1, then it becomes 1. So left limit, right limit, again left limit, right limit is hold. So that's why I am checking it is continuous, but it is your part. You may continue it. Check continuity. Actually, this theorem is using a lot of theory, and I cannot tell you each and every detail. So I will try to tell you each and everything, but you are smart enough to deal with those things. Since zeta ay zy is bounded and continuous on domain R, now we know that if it is bounded and it is continuous, so according to this function kxyt is the kernel of the heat equation, and this function which is defined at t equals to 0 is defined is written with the support of this heat kernel for Vx comma t. So we can say that it is going to be the solution of the heat equation. So it will be satisfied the heat equation equals to 0 for x belongs to R and t lying between 0 to t, where the initial data is defined as x of z of x. So this was the part. If you have doubt till this point, then please do ask to me. Now let m of a be the maximum of this initial condition g of x on mod of x is less than 1. Now using the inequality, if you will use this condition, then you will get the inequality kxy comma t is less than or equals to 1 over square root 2 pi e mod of x minus y for this heat equation, and you may derive this inequality for all x comma y belongs to R, x not equals to y, t is greater than 0. To prove this inequality, what you will do, let me give you a way. What is the form of this heat kernel? This kxyt is defined as e to the power. Just let me forgot about that. E to the power minus mod of x minus y squared over 4t into 1 over 4 t to the power n over 2. So you can use this part to do this. This is your homework. Using the inequality, we have that for mod of x is greater than a, 0 is less than or equals to v a, x comma t is less than or equals to m a, by t dy, that is less than or equals to 2 ma into a over root 2 pi e into 1 over mod of x minus a. Again, this thing is less than or equal to this on modulus of x less than or equals to a. So you can write it minus a to a. This quantity k dy will be less than or equals to minus a to a 1 over square root of 2 pi mod of x minus y dy, and then when you will take the integration over this integral, so this is not an even function, so it is not going to be 0, and this integration will be coming as this. Now let epsilon is greater than 0 and let rho is greater than a plus 2 ma over epsilon square root 2 pi a. Then va x comma t is less than or equals to epsilon is less than or equals to epsilon plus mu x comma t for modulus of x rho is equals to rho, and the time is lying between 0 to capital T, and v of a x comma 0. So this initial condition is defined as zeta ax comma into gx, and gx is the initial data for x. So this is going to be less than or equals to if we remove this term. So this is going to be less than or equals to g of x, and that is like this g of x is basically u of x comma 0. So if we add some positive quantity of epsilon, so it is going to be less than or equals to 0, because you know that this is given. So if you add a positive quantity, so it is going to be greater than or equals to, for mod of x is less than or equals to rho. By the weak maximum principle, t for modulus of x is less than or equals to rho, and time is lying between 0 to capital T. Now let this rho is tending to infinity. So basically this radius, nothing mod of x equals to r, this radius is tending to infinity, like we are covering the whole domain R, and we find the same. Yeah. Hi. Can you hear me?
Yeah.
So just give me 5 minutes. I have to change the socket of the electricity. I think there is some low electricity. So just give me 5 minutes. I will be back. I need to change the socket of this iMac. There is some electricity issue going on from last 1 week, and today everything is becoming finalized. So just give me 1 minute. Don't leave the class.
Sure.
Problem.
Bounded functions of a, we find that v of x comma t is equals to limit a tends to infinity v of a x comma t is equals to r k x y t zy dy exists for x belongs to R and the time domain 0 to t, and this is greater than or equals to 0 and but less than or equals to uxt. Furthermore, as v of a x comma t is less than or equals to v of x comma t is less than or equals to ux comma t for x belongs to R and t belongs to 0 to t. It also follows that v of xt is continuous on R cross 0 comma t with v of x comma 0 equals to z of x. It means using this inequality, and this inequality, you can say that u of x comma t is greater than or equals to v of x comma t, that is equals to integration over r k x y t zy dy r u of x t is greater than or equals to integration over r k x y t zy dy. So this was the first part of our theorem. In the second part, we are going to assume that w equals to u minus w equals to u minus this term, and this will be identically equals to 0. So let's proceed towards the second part. Second part is really very big and I am feeling lazy to prove the second part. Well, let's proceed. Now for the second part, let w equals to u minus v, which is continuous for x belongs to R with wt equals to wxx, w of xt is greater than or equals to. We know that if u is a solution, v is a solution, then their linear combination u minus v is also going to be a solution. And since u of x comma 0 is z of x and v of x comma 0 is z of x, so u of x comma 0 minus v of x comma 0 is going to be zx minus zx, so that is equals to 0. But in the last class we proved that the solution was unique when we have a bounded boundary. So if this was going to be 0 on the bounded boundary, so using the maximum principle, we could simply say that, oh, so it is going to be a unique solution. So that is uh, bounded, that is the solution w equals to 0 on the boundary. So using the maximum minimum principle, we can say that w equals to 0, that is u equals to v. But here we don't have a bounded boundary, so we simply can't use the maximum minimum principle, or you can say that is strong maximum minimum principle. So we have to be very careful here. Rather than w x comma 0 equals to 0 is satisfied, but we can't use the maximum minimum principle. So that is the drawback when we have the unbounded boundary. And w of x comma 0 equals to 0. Now it remains to show that w is identically 0. That is, we reduce the given heat problem, given heat problem to the case z equals to 0. Now we introduce a new function, say w of x comma t equals to 0, 0 to t, w of x comma s d of s. So if we are introducing this function, say this is equation number 3rd, just for the convenience we can use it. What is the time derivative of this function? Can anyone tell me, using the fundamental theorem of calculus? W. Simply, I suggest you something. When you will be taking the time derivative, and isn't it, it is the integration with respect to time. So the integration will be cancelled out with the derivation, isn't it?
Yeah.
So I was just checking your mind. Sorry. Not sorry. You should be thankful to me because I was just checking the presence of your mind, how you are operating in the class. And capital W are non-negative continuous on r cross 0 comma t. So capital W are non-negative because small w is greater than or equals to 0, and we are taking this integration over the increasing time. The integration of a positive function over the increasing domain, it means capital W are also going to be a non-negative continuous function on r cross 0 comma t with what will be the value of this wx comma 0, capital wx comma 0.
0.
Exactly. So you have two information. We are defining capital W in such a way that the time derivative of this capital W is small w, that is the solution of the heat equation, and also this W is 0 at time t equals to 0. Now the existence of Wxx is not obvious, since I wanted to ask you one thing. Um, would you please read it yourself, because this is using a very basic of real analysis. Now we are just going to use the this condition, or shall I prove it whole? What would you say? Just be confident what you want. Shall I prove it all, or you will take a look at yourself by yourself? Hmm? Camilo, Ivan, Roberto. What would you guys would say? I have given the proof in a detail in your notebook. So would you take a look yourself, or shall I prove it all?
I can read in the notes, I think.
Yeah, but like it is very simple. If you are confused at any point, I think it is going to consume a lot of time of me, because I can feel that we are defining a very basic of real analysis here and we are proceeding. So the most important thing was to define the basic things. So this thing was important to discuss, because you might get confused how we are saying non-negativity and how. So this thing and this part was little bit difficult. So I have completed this part. Now for the rest of the part, the author is using the basic of real analysis, and you can go over that and you can take a look and continue. If you are stuck at some point, then please do ask to me. I have written everything in the notes which I have uploaded today. Now let's come to the regularity condition. If you are stuck, then please do ask to me. Tomorrow I will ask the same question to you. So in the regularity condition, we are going to say that if the solution of a heat equation is if the solution of the heat equation exists and also its second order derivative is continuous, then u is going to be infinitely continuous inside the domain, and this regularity assertion is valid even if u attains a non-smooth boundary values on the boundary of this domain. So let me write the theorem first. Let the heat equation is same, ut minus uxx equals to 0. This omega t is defined as omega cross 0 comma t, where omega is contained in Rn. So if I am saying that omega is contained in Rn, so it will not be uxx, rather than it will be Laplacian of u. If omega is contained in R, then it will be a one-dimensional heat equation. So this is the domain. Always keep in your mind how we are defining the domain of the heat equation. So domain is defined as omega cross this capital T basically represents the final time. So let u belongs to C1 to omega t, solve the heat equation in the domain omega t. Then u is be belonging to C infinity omega t if u is a solution of the heat equation in such a way that the second order derivative of this u is continuous in the domain omega t. We are not talking on the boundary, in the domain omega t, then the infinite derivative of u is going to be continuous in the domain omega t, and this regularity assertion is valid even if u attains a non-smooth boundary values on the boundary of this domain omega t. Let's start the proof of this theorem. So consider the closed circular cylinder called a parabolic cylinder. Every time when we say that it is called a parabolic cylinder, this is just because this heat equation is parabolic according to the theory of discriminant. So this equation, heat equation, is parabolic, so its shape is going to be parabolic. So basically it is going to vary over a parabola. So that's why we are defining the cylinder. So we are defining a parabolic cylinder. So consider the closed circular cylinder called a parabolic cylinder, defined as C x comma t comma r such that y comma s, the pair y comma s, y is coming from the spatial domain and s is coming from the time domain, and this is satisfying modulus of y minus x is less than or equals to r, and t minus r square is going to be less than or equals to s is going to be less than or equals to t. We will take a look at the geometry. Oops. Just give me 4 minutes. I will be back. Just give me 4 minutes. Be here. Yeah.
Okay.
This is the parabolic cylinder, the closed parabolic cylinder. Yeah. So for the time domain, if you are assuming that this axis is time axis, if you are assuming that this is your time axis and this is your spatial axis, so this time axis is going to satisfy, this is at some time t, and this is t minus r square. I haven't uploaded it in today notes, but I will upload it shortly. I have made the notes, but I forgot. Yeah, so in the time domain, it is satisfying this condition, like s is varying between this, and y minus x is less than r. So this radius is basically r. So this is your C. Next, let me increase its surface. Yeah, in the same way. This is the easiest theorem you will go in the theory of the heat equation. I think the regularity condition is the easiest one because it is very easy to understand, in fact. And say this point is x naught comma t naught. Now this C that is defined as the closed circular cylinder, basically called a parabolic cylinder, because in this cylinder we are going to talk about the regularity of the heat equation, and the heat equation is a parabolic equation, so that's why we are calling it a parabolic cylinder. Now fix x naught comma t naught belonging to the domain omega t and choose the radius r greater than 0. This is radius r greater than 0 is small enough, so that C is equals to C x naught t naught such that R is contained in the domain omega t. So this is C x naught t naught R is contained in the domain. So if you are taking it as a center, suppose this is a cylinder. So the cylinder is a circular cylinder. So this is going to form a circle. This is going to form a circle. The end point of both end point of this circular cylinder is going to be a circle. So basically this surface is circle. So take x naught comma t naught this and the radius r and draw this circle, and same this point will be some x comma t because this is t and r. So now consider two small cylinders. Consider two. Please focus on the geometry, and if you are not getting a single point, then please do ask to me. Now consider two small cylinder. C dash is equals to C x naught t naught comma 3 4 r. It means the surface, the upper surface is same for this cylinder, and the other cylinder C double dash is equals to, in this cylinder, in these two cylinder, which one is going to be thinner? Can anyone tell me which one is going to be thinner, C dash or C double dash? Which one will contain C dash will contain C double dash or C double dash will contain C dash? Can you hear me?
The one below C double dash was the one with one half.
Mm-hmm.
One half R contains, oh no, 3/4.
Okay, so this is
3/4. See,
mm-hmm. So this is thinner, you are saying.
yeah, this is, yeah,
Ah, you are right. So okay, so it means C double dash will be contained in C dash, and C dash is contained in C because C has radius R. So R will be containing, R is greater than 3 by 4 R, and this is greater than 1 by 2 R. Today I will not be able to complete the whole thing, but you will have the pretty much idea, like the geometry should be clear. It is a very important theorem of this section. So if you will vary that r in this domain and in this domain, so height is also going to be less. So this is your C dash, this is your C dash. Now you know that C double dash has the half radius of this, so half of this, half of this. So this is C double dash and this was C. So you have pretty much idea about the geometry of this cylinder. Now let's talk about the theory. Now let's define the function. Let phi is belonging to C infinity Rn. It means, what is the speciality of this function phi? If I am saying that phi is belonging to C infinity Rn, can anyone feel the change? What is missing here? And psi is belongs to C infinity Can anyone feel the change? What is missing here? Please don't be scared. What you are feeling, just tell me. What is missing here and what is missing here?
Um, Missing where? In the phi and psi?
Yeah.
Da-da-da-da.
What can not
The do.
the domain?
Yeah.
It's
So
missing the
phi,
time.
yeah, phi
The
is
second.
independent of t. Phi is independent of t.
Hmm.
It means phi is defined as the initial condition and psi is independent of the spatial variable. So psi is defined as your boundary condition, isn't it?
Yeah.
So let phi belongs to C infinity. Every time in any theorem, if you are writing something, just notice what is defined and how why it is defined. So this is defined. This is very easy theorem. That's why I am saying that each thing is very clear. You already know all the things. Be such that the function phi is not exceeding 1 and it is 0 on the boundary b x naught comma r is an open ball in the spatial variable b x naught comma r is an open ball in Rn. So if we remove this ball, then phi equals to 0, phi will be 0 on the boundary. So just see how I am saying that. Just talk about 3D. We are free from t, so we don't have a time variable. So I am saying that I am constructing a ball x naught with radius r. Now this is your R3. So this is just a preview. So the solution phi is defined in such a way that phi is less than or equals to 1 inside this ball, and on the boundary this is going to be 0. This is just a way to define it, but it is in R3, so I am going to remove it because I am showing it in R3. Next, phi is strictly equals to 1 on the ball b x naught 3 comma 4 r. So see, what should I do here? I just wanted to show it here. Okay, so this is your x naught. T naught has been taken to be 0. So it may pass somewhere here. T naught is taken to be 0. So x naught is same, but T naught is taken to be 0. And the ball will be defined like this. Now it is saying that on this domain it is equals to 0. Inside this it is 1. If you define a ball with radius 3 by 4, like this ball that is contained in the bigger ball, this phi is defined to be 1 inside this ball. Inside this ball, this phi is defined to be strictly equals to 1. So these are some basic assumptions you need to understand it geometrically. And 0 is less than or equals to psi is less than or equals to 1 with psi of t equals to 1 for t naught minus 3 by 4 r square is less than or equals to t is less than or equals to t naught, and psi of t equals to 0 for now define a function zeta of x comma t. Actually, in the book of LC Evans, they are simply writing zeta of x comma t equals to, they are not decomposing it as a product of two functions, they are simply defining a function zeta such that the zeta equals to 0 on this, zeta equals to 1 on this. But I got another approach to write the regularity theorem in which we can define the function phi and psi separately, and then we can define zeta as the product of these two functions phi and psi t. So phi is a boundary function and psi is an initial function. Sorry, psi is a boundary function and phi is an initial function, because phi is defined as t equals to 0 or t equals to some t naught, and psi is defined at the boundary of the domain. Then zeta will be belonging to c infinity rn cross 0 comma t naught with zeta equals to, I will ask you what will be the value of zeta here. So Rn cross 0 comma T naught minus C. So what was your C? Your C was this function mod of y minus x is less than or equals to R and this. If I am excluding this C out of the domain, if I am excluding this C out of the domain, then what is the value of phi? 0. So can we say that zeta equals to 0 is going, zeta is going to be equals to 0 on this? Is it clear? And zeta equals to 1 on C dash, because when you will be taking uh, the consideration of t, then we can see that phi equals to 1 on this and also psi equals to 1 on this. So on this domain 0 comma t naught, phi and psi are 1, so zeta is going to be 1 on C dash, and on the rest of the boundary zeta is going to be equals to this. So the first part I have completed. This was the first part where we are defining this kind of function zeta, and how it is defined you have done, you know the geometry. So it is my request for the moment, please at least complete this part. So tomorrow it is the most important part to understand this geometry. If you are done with this geometry, so there is nothing in the regularity theorem, you already know the proof, it is very easy. So please go through this symmetry and how this zeta is defined with the help of the function phi and psi, how this zeta is defined with the help of the function phi and c. These two functions are playing an important role. So if you will go over the book, you won't be able to understand. But this thing here, from here, you can relate it to. So please go over that and try to understand. And tomorrow we will be completing the regularity theorem and we will go over the unit 2 again. So yeah.